All right, everybody, here we go. The last day of the Earth's History unit for our summer school session. I will be back on Monday, so make sure that any work that you have for our classroom from this week is completed and turned in, because that is going to be your grade for this week. Also, because it was kind of a lot, this is going to be a really good opportunity for some of you guys to boost your grade by having, really put some effort into these. All right, so today we're going to talk about absolute or radiometric or radioactive dating. So this is when we use radioactive decay to tell us the absolute age, like the actual, exactly how long ago did this happen, age of a rock or a fossil or an event like a volcanic eruption. Here we have our nice little rocks. We got some coal. They're doing a carbon date. All right, so absolute dating. So this is the use of radioactive decay to determine the exact age of a rock, a fossil, or an event. And radioactive decay is the disintegration of an isotope over time. So we're going to talk in a bit about some of the exact isotopes that we use in geology, but it's the decay of these isotopes is predictable, and that lets us use it to get the absolute age of things. All right, so in our relative dating that you practiced the last couple days, we know we have our oldest stuff on the bottom, our youngest stuff on the top, but that's it. That's the extent of the information we can get from that. Once we are using absolute dating with radioactive decay, we can tell the exact age of these different rock layers, not just their age relative to the layers around them. So by relative dating on the left, we would only know that our oldest layer is on the bottom, our youngest layer is on the top. With absolute dating, we can know that our oldest layer is 140 million years old, give or take by about 10 years, and that our layer up near the top is about 120 years old, give or take about 5 million years. So the radioactive isotopes that you have on your reference tables are potassium, rubidium, uranium, and carbon. Okay, this is where they are on your periodic table. So how do we do this? First off, geologists drill for core samples. So you got to get your samples of your rock that you're going to use and that you're going to date. You then crush that sample into a fine powder. So you need this powder in order to make this whole process work. You can't just take the age of these by the whole rock chunk, because what you use to do it, first you got to analyze for composition and inconsistencies. So you're going to analyze and be like, okay, what is this made of, right? And then you're going to use a spectroscope to measure the ratio of stable to unstable products. So the cool thing about radioactive decay is that it decays from an unstable isotope to a stable product. So it's that ratio that's going to tell us how many half-lives have gone on between this stuff being deposited or made and us trying to figure out how old it is. So an isotope, you guys remember from earlier science classes, is just a variation of an element with the same atomic number, so the same number of protons but different atomic masses. So our stable carbon, most of the carbon that we will encounter in our lives, has 12 mass units and is called carbon-12. The isotope that we use for radioactive dating is an isotope that has 14 units of atomic mass and is called carbon-14. All right. An important measure that you need to understand for radioactive dating is the half-life. So this is the time that it takes for half of the radioactive element to decay into a stable product. All right. So after one half-life, if you started with something that was 100% carbon-14, you would have half of that sample be carbon-14. All right. After another half-life, you'd be down to a quarter, and then down to 12.5%, and then down to 6.25%, and so on. All right, so every element has its own half-life, and that ranges from fractions of a second to billions of years. All right, we don't really have any fractions of a second ones on our Earth science reference tables because they're just not super useful for us in this field. However, we do have a billions of years option. Your uranium is a billions of years option. So as the proportion of your sample that is the parent isotope decreases, the proportion that is your daughter isotope, the thing we get after it's decayed, will increase, and they'll happen at the same rate. All right, so here's our little animation, right? We have uranium decaying to lead. And we see that as the uranium decreases, the lead increases at the same amount, the same rate. And eventually, we're left with no more uranium, or vanishingly small amounts of uranium, and all lead. Okay, this animation shows kind of the same idea here, but you can see that it doesn't happen with decay. It's not like one segment decays and it slowly spreads. No, like it decays kind of at random. All right? So we start with our blue, and these dots change to red, representing our radioactive decay. But you see, they don't like go left to right or top to bottom. It's at random. Right. So this is why we can use radioactive dating to get our half-life, right? The half-life of an isotope is not affected by any environmental factors. So temperature, pressure, chemical reactions, none of those affect our half-life, all right? The radioactive decay takes place in the nucleus, all right? The nucleus does not like to be messed with, all right? So nothing other than the actual process of our radioactive decay is going to affect our half-life rate. So one of the ones that we use when dating rocks that are really, really old, I've mentioned uranium. The specific isotope is uranium-238. It decays to lead-206, and the half-life is 4.5 billion years, right? So if our Earth is 4.6 billion years old, right? There are some things that might have some uranium in them that will have only undergone 1 and a bit half-lives, right? And here's just the whole decay path if you are super interested in it. Start with uranium-238. You have a whole bunch of different processes, and then we get to our stable lead. And you'll see here we have things that the decay process takes like hundreds of thousands of years. It's how we add up to our billion years. All right. Now, when we are talking about dating organic remains, we are looking at carbon-14. So carbon-14 decays from carbon to nitrogen, and the half-life is 5,700 years. So when we are dating things that were alive, organic remains, because organic stuff contains a lot of carbon. You and I contain a lot of carbon. If you guys remember from Living Environment, all of your organic molecules that you needed for life contained carbon. All right, so that's why this one's a good one for that. And here's the other ones that you have in your reference tables. So carbon-14 and uranium-238 we've already talked about, but we've also got potassium-40, which decays to argon and calcium, and rubidium-87, which decays to strontium. And we've got some different half-life lengths. Carbon-14 is a good one for relatively younger stuff, and the rest are good for our much older things. Potassium-40 with a half-life of 1.3 billion years. And we talked about uranium. Rubidium has a half-life of 49 billion years. All right, so I want you to think about these for a minute here. What would you use to date a human bone? Okay, which of our selected radioactive isotopes from your reference tables would you use for that? Next up, what would you use to date the age of the Adirondack Mountains? And finally, what would we use to date a trilobite fossil from the Devonian period? So in addition to doing some thinking, you might also want to look at pages 8 and 9 of your reference tables and do a little flip back. See how long ago the Devonian period was. See how long ago the Adirondack Mountains formed. And think about which half-life is on a time scale that could work with those. All right, so for the human bone, we would use carbon because most human remains are going to be on a geologic timescale relatively young, from up to 15,000 years ago. And the half-life of carbon-14 is 5,700 years, so we're looking at between 2 and 3 half-lives there. For the Adirondack Mountain, we're going to use uranium, right? Because that half-life, close to the age of the Earth, I've talked about it during our landscapes unit and maybe mentioned it a little bit during our metamorphic rock stuff, but the Adirondack Mountains are some old rock. So we want to use something that would get us to our long half-life to go with that old rock. All right, and for the third one, we were going to do potassium-40 because even though this fossil is going to be something that was alive, it's going to have been from so long ago that there's not really going to be any carbon left. But there's like a lot of potassium around the planet, right? So potassium can also work. So early fossils, right? Eurypterids, trilobites, dated to 50,000 years ago or older, we are going to use potassium for that. All right, you guys have 2 radioactive dating and decay assignments to do today and time to finish up any other assignments that you have from earlier this week. I would do the radioactive decay practice first and then the radiometric dating assignment, but you choose your own adventure there as long as they both get done and as long as you use your time wisely. This week should have been a helpful one for you. All right, guys, I will see you on Monday.